All right, so we've studied a thermal simulation analysis in some detail, both from a loads or usage in EUI standpoint and a production standpoint. We modeled PV production on the roof. So now we need to talk about benchmarking, and that's really very important. It's sort of the central reason that we're modeling it all. The idea is that, so benchmarking just means comparing something to a standard, so designing to a standard. And we set the standards. We decide ourselves what we want our level of performance to be for whatever metric we're choosing, and it could be anything. I mean, if we can find a metric to measure happiness, we can simulate that in some way. But the point is that we're going to create a program that has specific variables that we choose and benchmarks that we're trying to reach. And so that way, as you're working on your studio project, you can look at all these variables at the same time or check in and say, wait a minute, I just made a change. Let me check in quickly and see what my thermal performance is, and if I messed up something by making this change. And the idea is, if we don't do that, we'll never meet these much more stringent standards that are part of the world we live in now. Okay, so the first thing we should remember when we start talking about benchmarking is that we are in this kind of funny situation as designers in the United States because we use the IP system, inch pound, or IPS, inch pound seconds. This is a map of all the countries in the world that use the IP system. So the United States, Liberia, and Myanmar, with the UK still fudging a little bit and doing a mixed system, and they're the ones who started the whole thing. So that means that we have to be constantly on the lookout for the metric system, which is undoubtedly, it's just a better system. It's much more logical. So science uses it. Uh, Engineering in the U.S., both of those use metric. Most of the world uses metric for everything. So we have to get adept at, for one thing, noticing that, keeping track of units and seeing when they're metric or not, and also being able to convert. So I've made a spreadsheet to help us with that, and so let's just take an example, and I'll probably add to this as I go. This is just something I needed all these conversions as I was working on the materials for this class, and so I just have been building this little spreadsheet. But let's just take an example. So U value in IP. If I have a zero point 0.5 U value in IP units, that's going to be an R value of 2 in IP units. If I have a U value in SI units of zero point 0.5, though, it's a R value in IP of over 11. So it's a huge difference between these two numbers, right? And that's the same letter. And so if we don't have, if somebody's not telling us the units or that it's IP or SI, then we are, and often they won't, because we are in the minority in the United States, and unless they're trying to give us cut us some slack, they may just be talking about metric units. So you got to be conscious of that. Another reason I'm bringing this up right now is that I'm pretty sure that um, the value in Climate Studio, because they're converting from metric units to IP units, pretty sure that they've screwed up the conversion for carbon. And that's what we're talking about here in the benchmarking that we're getting ready to look into. So why do I say that? Well, we have an SI of kilowatts hours per meter squared converted to kilobtu's per square foot. If I open up my trusty spreadsheet here, let's see. So 196 kilowatt hours per square foot per year is 62 kilobtu's per square foot per year. That totally makes sense. But then if I look at the carbon values, 77, I already have it right here. So 77 kilograms per meter squared converted to pounds per square foot. They're getting 77 to 1820, and I get 16. So I think this should be 16 at 1820. And it's a pretty simple conversion. Kilograms to pounds is, we're multiplying here by 2.2 in the numerator, and then meter squared to foot squared is 10.76 times to get the feet squared. That's in the denominator, so it makes, it's like 0.2 or something, but it's a smaller number. All right, so We need to be conscious of that. And so then what I'm saying is we should just use the metric. And I've created a spreadsheet that will convert for us, so it should be straightforward. But just remember that don't use this value. And there's another value I found like that. So we'll just have to keep our eyes open. Um, okay, so let me go back to the slides. So what's our benchmark for this? There's a new law in New York City called Local Law 97. I've mentioned it before, and it creates very stringent carbon emission standards for any building. We'll talk about the specifics in a second, but let's remind ourselves why carbon. Unless you've been hiding under a rock for a while, it's climate change, and there is no debate about it. And uh, it's pretty well established that a lot of this crazy weather is climate change connected. But the basic science is so straightforward that it's kind of laughable that there's people that might still debate it. I think they're all politically motivated. Here's the only slide you need to look at. This is a U.S. government slide, NOAA. And what they did is they took all the data that we have from thermometers taking temperature around the planet, and we have that going back to like 1880. And so this is just thermometers. It's just somebody writing down in a notebook temperatures, and sure there can be mistakes, but this is science and it's redundant, and it's not a high-tech thing. We're just looking at numbers on a thermometer and logging them. And then what they did is they said, okay, we're gonna pick a year that's going to be the baseline, so it'll be 0, and then any of the average temperatures on those thermometers that are above that baseline are going to be, we're going to go above 0 this direction, and if they're below 0, or lower, we'll go below, and we'll graph it. So they picked 1940 as the baseline, and you see what we've got. Basically, it's been getting warmer, 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 and all the years before 1940 we're getting cooler. We're cooler, so it's definitely warming. There's tons of other, there's thousands of um, peer-reviewed papers we can read, but this is why we have this law, and you can't disagree with it anymore because it's just the law. I don't mean you, but I just mean this is just what we have to do. This is the standard of care now. This is legal design. So this is the law, Local Law 97. Basically, what it says is that any building in New York City that is 25,000 square feet or more, and that means that's already built also. So if you own a building and it's just sitting there, and it's 25,000 square feet or more, you fall under Local Law 97, which starts next year in 2024. And there are carbon emissions. So TCO2e per square foot is tons of carbon equivalent, carbon dioxide equivalent per square foot. An equivalent is taking into consideration other um, greenhouse gases, like methane, for example, has a much higher effect on temperature than carbon dioxide, but just we're putting so much more carbon dioxide into the atmosphere. It's really the only one we have to, or the main one we have to worry about. If we don't fix the carbon issue, the rest of it's moot. And then there's two parts to this. Well, three parts really. One is, so we have it in the building code now. I'm not sure why my mouse is locking up. It's always the way, right? We have uh, intensity emission intensity limits per square foot based on building types. And these building types are, based on those DOE building types, or they are those DOE building types that we discussed at one point in class, or I mean, or in these videos. We've been dealing with the medium office for the models that I've been giving as an example. I also did an apartment building at a mid-rise apartment with a single. We were dealing with one apartment in a mid-rise apartment building. But anyway, so these are the benchmark. Uh, actually, I'm going to confuse you there. Those are the DOE prototypes, and they're represented in this column. If you were using the DOE Property Manager website and tool, you would have a different set of values than what we're going to use. We're going to use just what's comes straight out of this document, and I have a copy of it that I'll share with you if you want to look at it. So we're saying that for example, the office we've been doing, um, so this is the DOE categories, and these are code categories. So this is what we're used to in terms of egress. A3 is a museum, B is an office. So for what I'm doing right now, I'm going to use the B number. It's 0.00846 tons of carbon equivalent per square foot of building space. So I have another page on my spreadsheet here that has local law 97 inputs. And let's talk about this briefly. First, we have the energy use categories. So that means fuel oil, number 2 and 4 as examples. These are common in certain types of buildings. Natural gas is the MG. Steam would be district steam, and electricity. And so this, these are used both, of course, for plug loads, like whatever you plug into an outlet, but also heating and cooling, hot water. And so one thing that we obviously want to keep track of the cost of these things, and so we can do that as part of this calculation. But the other thing here is that each of these fuel types has a different carbon equivalent, essentially, a calculated amount of carbon per unit of energy. And so that would either be kilowatt hours or kilobtus. And why is that? Well, electricity, for example, which for certain reasons we're trying to switch over to more. One reason is because we can make electricity with the sun's photovoltaic electricity, which is very low carbon. But this energy source, it has a downside if it's produced centrally, like at a power plant somewhere, because there's a lot of loss of energy when it comes to the site. So you have often you're burning coal to turn a steam turbine to produce electricity, and there's a lot of friction and other losses in that production process. So, and then you're putting it onto these distribution lines that have just basically a lot of friction. Resistance, electrical friction resistance, to get that energy to the site. So it's a less efficient source of energy than these others. But these others are actually burning fossil fuels, so they are by definition finite, whereas electricity can be infinite if we're using things like solar or hydropower. But so we have to then determine what portion of our loads are being correspond to which of these fuel sources. And so these are from the code here, and then I've converted them to both pounds of carbon per kilobtu and kilograms of carbon per kilowatt hour. And I've done that conversion because these are the numbers that are in Climate Studio. And another thing I should say about any of these spreadsheets, you'll see down here this little key. The way I've got this locked, let me show you. So it's protected, this sheet, which means, and I'm doing that just so we don't mess up the formulas that are in here. So any blue cell you can change. So let's go back to these, right? So when I was here, I could change this cell in blue, but I can't access these cells. Now maybe that's a little bit of so I'd like you to be able to see these formulas in here that I've put in. So maybe we'll consider, I may change this, but right now that's the way it works. But even if they aren't locked, the idea is that I'm color coding so what where the inputs go, and then the yellow are outputs, and the oranges are sourced from the code. If that's confusing, we can talk about it. It's really very straightforward. You're just going to be plugging in a couple of numbers, but I wanted to give you the background. So we're saying we have to identify the fuel source so that we know how much carbon it has per unit of energy. Then we have different allowances for carbon per square foot based on the occupancy type. So, for example, museum has a higher use allowance than a business, right? And this again is in tons of carbon per square foot. And then finally, this is the standard is going to become more and more stringent as we move forward towards 2050. And essentially in 2050, the goal is to be essentially carbon neutral. So we can design a building in 2024 that will or that will meet the requirements in 2024, but it would fail in 2030 and 2050. So we have to be thinking about the future as we're designing now. So let's take a second to see what this means. There are a number of tools that are available for us were created by the city, New York City. And so this is a cool one. It's an interactive map, and we can put in projects or addresses in the city. So I'm going to put in Guggenheim Museum, and it will take us to the project. And if it's been recorded, then it'll give us the basic information about it, and tell us what the fines are going to be. So the Guggenheim Museum, according to this map, is going to be fined $215,000 starting in 2024 unless it upgrades. And this is where you remember I've talked when I was introducing some of this in other videos. They're going to be able to accomplish a lot of that, or maybe all of it. Hopefully, they'll have to do all of it with the mechanical systems, because you're not going to go wrap the Guggenheim Museum in insulation. You may change the windows, the glazing. So anyway, it's an interesting that even the Guggenheim is on this list. Our building at NYT uh, is also here, and we are a much more up-to-date building, but still in 2024 looks like we're gonna. So next year we would owe $11,000, and moving forward it's going to be a lot more. So I haven't talked to anybody about it, but I'm assuming that there's plans in the works to make this upgrade and save that money. And then maybe the final thing to say is we can make a point by looking at this other calculator that's available, and I'll share with you. Uh, the main, and this is people are really scrambling in New York City to deal with this. The Most of the discussion or the concerns or the people that are trying to figure out how to do this is in the case of existing buildings. And so typically people are going to have energy bills, and so they know how much energy they're using based on because they're paying for it already. And so that's what this tool allows you to do. If you owned a building and you said, okay, it's an office building, it's 100,000 square feet, and I use this much electricity based on my bills, um, and then we see what the threshold is. We can either normalize means per square foot. We can look at if we go back and look in the chart, that number is going to be there. I think that's the one from not from the city, but from the project manager site that I was telling you about. But anyway, these are standards, and we would do the same for all of our other fuel types. And so one of the strategies here, actually, let's just they have a sample building. So it's and remember these are just the code building types. Which are going to set these threshold values internally here based on the square footage. So this is just a little spreadsheet that's got a nice user interface and output. But so if we look back at our this spreadsheet, natural gas has by far the lowest. Actually, not steam. I'm not even sure if this is right. I'm going to check into it. I really think that natural gas is lower, but anyway, maybe not. Whatever. I'll check this. The point is, you could definitely fuel oil is higher than natural gas, right? So your first strategy might be to try to get any of this. If there was any fuel oil use, you try to get it into natural gas, or maybe you would take some of your electricity uh, and get a natural gas boiler rather than a electric resistance water heater. So a lot of the work can be done just adjusting your mechanical systems and making them more efficient. Um, but okay, so how are we gonna? The issue we have is that we don't have energy bills. We're designing a new building, and so what we have is our outputs from Climate Studio. So let's just, we really haven't looked at that yet, so let's go look at, or not very closely, or not in a while. Let's look at, go to my thermal analysis tool, and just look at edit one of the zones, and go to settings. We see here that under carbon and cost factors, we have a variety of carbon dioxide categories: heating CO2, cooling CO2, hot water CO2, and electricity CO2. Now, why would we have these? It's because if we define a specific kind of heating system, it's going to maybe use fuel oil or natural gas, whereas if we have um, a certain kind of air conditioner, that's going to use electricity. And so we'd want to be able to adjust these numbers based on that. And then, of course, the cost we want to be able to adjust based on real world numbers, which are changing all the time. By the way, you can just skip this zone behavior stuff. These are going to be presets that are beyond our skill level to change. Um, so that's where we are getting the carbon and cost numbers that are in our results. So, the site EUI generates the carbon number from based on saying, oh, well, you chose this kind of heating system, so we're going to say that that's natural gas or steam. We don't control that. So this is not a super detailed energy model, but we can mess with it by how some of the mechanical settings we change. Like if I set my heating system to a COP of 3, that's definitely going to be an electric system, and I'm assuming that this model understands that and will put that in that category. Regardless, we're just going to take our carbon number straight from this. We don't have any energy bills. We haven't built this building, so we're just going to take these numbers and use them as our bench for our inputs for our benchmarking to see. And so our goal is going to be to design a building that meets the local law 97 requirements. So it would be legal in New York City, which is where you guys are designing your studio project. So then, let's do that. Here I have created a spreadsheet for us to use for this purpose. It's pretty much completely automated, so it's pretty straightforward to use, and let me show you how to do it. If I go to, let's say, okay, we'll start just by, I'm going to put in these runs. So I guess let's just go ahead and get official about it. I'm going to give it its name, TX. This was an office building. This was that medium office building that we were designing. These are different runs that I did for a different purpose. So I'm going to choose B. And so when I do that, we see that the values for carbon per square foot populate from the code, but they're not in they're not in tons, they're in pounds, because we have pounds in our IP units, or kilograms or pounds, right? So I am setting this up so that we don't have to do any conversions, or you don't have to do any yourself. But you should try to understand what's going on at least. Okay, and now I'm going to the building area. I can't remember. I think it was 46,875, something like that. I would maybe go ahead and put in this name. And what this is saying to me is this is a 90.1, so an ASHRAE 90.1 standard building, medium office in climate zone 4, and all these zones are set to one use type. All is open office. So I'm going to put that in here. And so what happened when I did that? As soon as I put in this value, let me delete it. If I put in a value of, let's say, 24,000, we can still run this, but it's not local law 97 applicable because it's below 25,000. But if I put in my 46,875 or whatever it was, then this does apply. Now I'm going to put, now all I have to do is, and again, I'm just inputting into the blue cells. So what do I want to put in there? Let me get this out of here and leave that there. Okay, maybe I can just do this. I want this full size. Okay, so I've got 95 kilowatt hour EUI and 53 carbon kilograms per kilograms per square meter. Anyway, so what was it again? 95, 53. Okay, so I'm going to put in my 95 EUI, hit enter. That populates. So now I have a total kilowatt hours. So if I need that for something else based on my square footage, now I've converted to kilobTUs per square foot. And PV we're going to add in later because remember we calculated how much PV we might be able to produce on our roof. And then and the total is going to be this minus this. So we'll see the total amount of energy that we're using if we have some PV to replace some that we're buying. And then what was the carbon? Was 53. And so we see that this design, whatever it is going to pass in 2024, so that's good. But then in 2029, it's already not passing. In 2050, we're definitely not passing. But what if I then could make the 26 kilobTUs per square foot of PV power? Then I am passing in all three. So that's the process. We get our loads as low as we can get them, and then we bring the PV in and see if we can have a total usage on site that gets us to pass. And so, I can just keep doing that. Let me do one more. TY in, let's see, is that any different? No, it's not. This is it. So and this one looks like I have the same settings, but I made one of them a meeting, or some of the zones a meeting instead of an office space. Oops. Maybe that's just okay. And these settings will be the same. So this is a drop down, by the way. You can select whatever occupancy type you want, and it will populate automatically. If anybody wants to learn how to do these things, we'll be happy to teach you. It's the same buildings, the same square footage, and we're at 99 and 56. So that's probably about the same, right? Yep. So we're the same situation. Probably if we add our PV, yeah. So this building's in good shape if we add PV, and so that would mean we'd be arguing or making the argument to our client that we wanted to be planning for PV, and we're at the beginning of the project, so that's a possibility as opposed to waiting to the end. So let's look at then is the last thing we're going to do on this. Let's just look at this is all those runs that I did. Remember so this was that building. It had a bunch of funky shading, had this glazing set up, and then I ran just a ton of different simulations, starting with a 1960s envelope with an old school mechanical system. And so this is the results. And we can see that, a 1960s building is not going to make it. Once we start upgrading the mechanical system, Okay, so like again, this is now we're thinking about well, maybe the Guggenheim. We really get to work on the mechanical system. We might be able to make it at least for the to get buy some time to get to 2029, and then it keeps going. So we could just well, and that's before any glazing. So let's see, the 1960 with the default glazing and the decent envelope. I mean the decent mechanical system. No way, nothing's working here. Um, if we improve the glazing still not going to work. So um, we'd have to do a lot of work on the Guggenheim to figure out how to make it function. But these more contemporary buildings are doing pretty well, right? So we're on all of them. Once we get to the 90.1, we have windows and we can have shading, and then we're passing at least for the current year. When we get down to the passive house stuff, where we have a better envelope and lower infiltration, natural ventilation, we're in compliance at least through 2030. And then if we add in um, let's just add our PV in the whole way, we see that, PV just would not have been of much help to the 1960s building, but it helps with a lot of these. So if we get our loads down to a decent, with a decent effort, we can add photovoltaics according to this model and pass and build a local law 97 compliant building and save the world from climate change, and not get sued. All right, so that is the full uh, thermal simulation coverage. We did loads, production, and benchmarking. Now let's move on to daylighting, and that's a whole other can of worms, and it will be interesting to see how we can make our thermal and our daylighting designs come together.